Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. So in the last video we spoke about splitting fields, and so let's recall the definitions involved with that. So if we have a field K inside another field L, and we have some polynomial f of x whose coefficients are in K, then we say that f of x splits in L if it factors in L adjoin x into a product of linear polynomials. And so what this means is that all of the roots of f of x are in L. Then from there we can define a splitting field, and so we'll say that sigma is the splitting field of f of x over k. If f of x splits in sigma, and that sigma really is the smallest field that f of x splits in over k. And so the way that we express that is if f is some field over k that also splits, where f of x also splits, then sigma must be a subfield of f. And a consequence of this last one is that sigma, let's make that a little bit smaller, is going to be equal to k adjoin alpha 1 through alpha n, where alpha 1 through alpha n are the roots of f of x. Okay, and so that's what sigma has to be. And then the big consequence of this that we saw in the last video is what we call the isomorphism extension theorem. And it says that if you have an isomorphism between two fields, k and k prime, and you have some non-zero polynomial f of x over k, and sigma is the splitting field of f of x over k, then the extension sigma over k is going to be isomorphic to, we're going to call it sigma prime over k prime, where sigma prime is the splitting field of phi of x, so this is what f is sent to when phi is applied to it, over k prime. And really the main use of this that we're going to be using really comes from a corollary that ties this to Galois groups, where we're kind of thinking about sigma and sigma prime being the same splitting field. And that says that if f of x is an irreducible polynomial over k, and alpha 1 and alpha 2 are two roots of f of x, then, and we let sigma be the splitting field of f of x over k, then there's going to be some element of the Galois group of sigma over k. So there's some automorphism of sigma that fixes all the elements of k such that sigma of alpha 1 is equal to alpha 2. So alpha 1 is sent to alpha 2. And so there's this sort of transitivity of the roots of irreducible polynomials inside of a splitting field, in the sense that for any two roots of this irreducible polynomial, there exists some element of the Galois group that sends one to the other, and there's some other element that does the inverse. So what we're going to be talking about in this video is what are called normal extensions. And so we say that an algebraic extension L over K is normal if every irreducible polynomial f of x and k of x that has at least one root in L splits in L. So you can think about normal as being like a splitting field on steroids in a sense. That for a splitting field, you're talking about one polynomial splitting into all of its irreducible factors. In a normal extension, if an irreducible polynomial has one root in the extension L, then it has to have all the roots there. So an example of this is if we look at the degree 2 extension, q adjoin the square root of 2 over q, this is a normal extension. And if we let f of x be some irreducible polynomial over q, over the base field q, and suppose that it has a root in q adjoin square root of 2, well, the root, since it's in q adjoin square root of 2, it has to look like a plus b times the square root of 2, where a and b are two rational numbers, because that's what everything in q adjoin square root of 2 looks like. And so what we need to show is that this f of x actually splits in q adjoint square root of 2. And if we know that one root is a plus b square root of 2, then it has to be that the other root is going to be a minus b square root of 2. And this is just because when you multiply, when you take these two linear factors coming from a plus b, and that's this linear factor, and a minus b, giving you this linear factor, you get this quadratic. And because we know what the roots are, we know that it doesn't split in q, and so it must be splitting in q adjoint square root of 2, because both of these elements are in there. And this is true for any element in q adjoint square root of 2 that's not in q. We can do this process. And so all of their irreducible factors, all of their minimal polynomials over q are going to split in q adjoint square root of 2. So just to reiterate this, an algebraic extension is normal if every irreducible polynomial that has at least one root in L splits in L. So let's think about what this means. If we have some alpha in L and we let f sub alpha of x be the minimal polynomial of alpha over k, well then that means that f sub alpha splits in L. So it turns into a bunch of linear factors. And so these linear factors are going to be all the roots of f sub alpha. So L is going to contain all of these roots of f sub alpha of x. And so that means that L must contain the splitting field of f sub alpha of x over k, because f sub alpha has split. And so this is one of the properties of a splitting field, is that if you find some field in which the polynomial splits, then the splitting field must be a subfield of it. And so in particular, if we applied this, we had our base field be the rationals. Well, if alpha is in L and L is normal over the rationals, that means that for anything in L, any alpha in L, L has to contain all of the conjugates of alpha. Anything that alpha could possibly be sent to in a Galois group would have to be inside of L. Okay. So the big theorem for this video, and this is actually one of the most important theorems for the course. This is really is a culmination, and this is really going to be critical when we go and prove our fundamental theorem of Galois theory, not too far away, is the following. And it says that normal extensions are splitting fields, and splitting fields are normal extensions. And so a finite field extension L over K is going to be normal if and only if L is a splitting field for some polynomial over K. Right? And so remember we talked about earlier about normal polynomials being like splitting fields on steroids, and essentially what this theorem is saying is that any splitting field is a splitting field on steroids. So let's prove this. The forward direction is pretty straightforward, because really if you think about it, normal is perhaps a bit of a stronger property than being a splitting field. And so if we have L over K be a finite normal extension, then since it's finite, we can write L as being K adjoining some alpha 1 through alpha n. This is a property of L over K being finite. Well, then we can just take the minimal polynomial for all of these alpha j's that we use to generate the field extension. We're going to let our f of x be the product of all of these minimal polynomials. Well, then f of x is going to split in L, because this is what it means for L to be normal. So since it has alpha 1, that means that the minimal polynomial for it, which is n1, has to split. Since it has alpha 2, that means that the minimal polynomial for alpha 2 has to split. And so it goes through for all of the mj's, and overall we conclude that f of x has to split in L. So the splitting field for f of x must be inside of L. On the other hand, L must also be inside the splitting field of f of x, because L contains, if you look at how L is written, it's k adjoin some of the roots, and the splitting field would just be k adjoin those roots and some other ones, and so L must be a subfield of it then. And so that means that you have this double inclusion. L contains the splitting field, but L is also inside the splitting field, and so L and the splitting field are equal. So L is going to be the splitting field for this f of x. And that finishes this forward direction. Now for the backwards direction, and this is going to be a little bit more complicated. So we're going to start with a splitting field for some f of x over k. And so again, we're going to have L is written as k adjoin alpha 1 through alpha n. Now what we need to show is that if we have some other beta in L, its irreducible polynomial is going to have to split in L. And so that means that for any other root of its irreducible polynomial, it's going to have to be in L again. So the way we're going to approach this is we're going to take g of x to be some irreducible polynomial with a root in L. So g of x is an irreducible polynomial over k, and we know that the root beta, one root beta is inside L. And then we're going to take another root gamma of g of x, and we want to show that gamma is in L as well. And so if we can show if this is true for any other gamma, that's going to mean that all of the roots of g of x are inside of L. So we're going to create a splitting field sigma, and what sigma is going to be is it's going to be f of x times g of x. And so this is going to guarantee that it has all of L, because it has all of the roots of f of x, but it's also going to have all of the roots of g of x, right? And so we're going to have that L is a subfield of this sigma, and we're forcing g of x to also split in this sigma. So sigma is going to be the splitting field of, I need to include in here, f of x times g of x over k adjoin beta and k adjoin gamma. And that's because since sigma is the splitting field over k, and k adjoin beta and k adjoin gamma are both subfields of sigma over k, this is one of the properties that we saw in the last video, that any of these intermediate fields, sigma must still be the splitting field over it. And so we're going to let phi then be, there's an isomorphism between k adjoin beta and k adjoin gamma that comes from the fact that they're the roots of the same minimal polynomial, g of x. And so we have some isomorphism, phi, that's going to send beta to gamma, and phi is also going to be the identity map on k. So if we restrict phi to k, it is the identity map. So phi fixes all the elements of k, and it sends beta to gamma. Now we will apply the isomorphism extension theorem, and that is going to lift our isomorphism phi to an isomorphism psi from the splitting field sigma to itself. And so really it's going to be an isomorphism, an automorphism on sigma. And psi here, by the isomorphism extension theorem, if we restrict psi to k adjoin beta, then we get phi. And so this means in particular that psi, if we plug beta into psi, we're going to get gamma, because phi of beta is equal to gamma. And it also means that psi is going to fix all of k, because phi fixes all of k. And so if psi fixes all of k, then this means that it actually is a k automorphism on sigma, because it's an automorphism on sigma that fixes all of k. Now since beta is in L, and L is equal to k adjoin alpha 1 through alpha n, that means that we can write beta as some linear combination of powers of alpha 1 through alpha n. So there's some way to write beta like this. And that's just, this is what the elements of the basis of L have to look like. This. And so we can write beta like this. And where each of these CJs are going to be in our base field K. So we have that gamma is equal to psi of beta. And so beta, we just saw that beta is a linear combination of these monomials in alpha 1 through alpha n. And so we can write it like that. Now psi is a field automorphism, and so it's a homomorphism, and so we can distribute this psi, and psi is going to fix all of the CJs, because the CJs, these are in K. And so then we're really just looking at psi applied to alpha 1 through alpha n. So gamma is equal to C sub j, the sum of C sub j times some psi of alpha 1 to some power times psi of alpha n to some power. Now let's think carefully about what psi is going to do to each of these. So for each j, alpha j and psi of j are going to have the same minimal polynomial. And that's because psi is an automorphism on sigma, and so it's going to send elements to other things that have the same minimal polynomial. This is a property of automorphisms that we've been using for quite a while. And so since alpha j and psi of alpha j both have the same minimal polynomial, and those minimal polynomials split, they have the same minimal polynomial over K, and they split in L, that means that psi of alpha j is going to be inside of L for every j. And so what this means is that this is in K, which is a subset of L, and then each of these are in L. And so really we just have a linear combination of things in L. And so that implies that this entire sum is going to be in L, and this entire sum is equal to gamma. So gamma is inside L, and so since gamma is any other root of g of x, this means that g of x is going to have to split in L. And this completes our proof. So just to reiterate what this theorem says, that a finite field extension L over K is normal if and only if it is a splitting field for some polynomial over K. So being normal is equivalent to being a splitting field. So what's the importance of this? Well, as we talked about, being normal is a powerful and useful property. So in particular, it means that if you have some L over K is normal and F is some field above K, and we take some element of the Galois group of F over K, well then, if we take anything in L, sigma of alpha, any alpha in L, it's where it lands in from the using the Galois by applying the element of the Galois group. So sigma of alpha is going to have to be in L as well. And I'm not going to go too much deeper right now into this because this is going to be one of the homework problems, or essentially one of the homework problems for this week. Explaining exactly why this is true. And so this is the power of being normal. On the other hand, being a splitting field, this is a much easier condition to check, because rather than having to see whether everything splits, we only have to focus in on the generators. Once we know that it's to show that something's a splitting field, we only have to focus on the generators that create the field and check that their polynomials split exactly. And so being normal is very powerful. Being a splitting field is easy to check. And so putting these together is very powerful because it means it's both powerful and not too bad to check. Okay, so once we have this idea of normal, we see that it's nice to be in a normal extension. And so this breeds the idea of what we call a normal closure of an extension. So if we have that L over K is a finite extension, then we're going to say that the field N is the normal closure of L over K if N contains both L and K, N is normal over K, and it really is the smallest normal field that contains L and K. So if M is in between L and M over K is normal, then M is equal to N. And so what this last one is really saying is that N is the smallest normal extension over K that contains L. Okay, and so that's really the idea of the normal closure. It is the smallest normal extension over K that contains L. So here's what I just wrote down in much easier to read print. So our final theorem for this video is really saying that normal closures are unique. So if we have L over K as a finite extension in C, in the complex numbers, then there is a unique normal closure of L over K inside of C, which is the finite extension of K. Okay, and so we know that L over K is normal. So to prove this, we're going to start off by saying we're going to let L be K adjoint alpha 1 through alpha n, and then sort of same trick that we did before, we're going to let M sub j be the minimal polynomial of alpha j over K. And so then we're going to create polynomial f of x, which is just the product of the minimal polynomials, m1 through m sub m. And then we're just going to define n to be the splitting field of f of x. And so this is going to guarantee that n is normal over K. And so then the last thing to check is just that it's the smallest one. Right? So thus n over K is normal because n is a splitting field. This is using the fact that being normal is equivalent to being a splitting field. And if we have some other normal extension m over K, so we're kind of following the definition here, if L is inside of M, then N has to be inside of M as well, because M has to contain all the roots of f of x. Right? And that's how we defined N. That's how we created N. N is the splitting field for f of x. And so anything that contains all of the roots of f of x, well, that means f of x will split in it. And so the fact that N is the splitting field for f of x means that N is going to be a subfield of M. And so this shows that N is the unique normal closure. If you tried to create a normal closure in any other way, you'd end up with the same N. You'd always have N being the splitting field of f of x. It has to be that. So N is the unique normal closure of L over K because any other normal closure would have to contain N. Any other normal extension of K that contains L would have to contain N. So this finishes the proof. And we'll see that normal closures are a nice thing to have. If you're given some extension, you often want to have normality is just such a nice condition to have. And so if you're in an extension, oftentimes you'll just go up to a normal closure because now you have all of the benefits of working in a normal extension. That is all for this video. I will see you again soon.